Today we're going to look at this model here. This is one of our examples that we ship with the product. Now it's a pretty small model, but it does have quite a bit of distribution network out here, mostly junctions, demands, and so forth. There is a pump station here that pumps up to a tank at this point over here. So this is the full version of the model. So you could go with this, or let's take a look at the skeletonized version of the same model. So you can see, and I'll switch back and forth one more time. So these are hydraulically equivalent models. So if we were to look at this skeletonized model, for example, looking at the pump and the tank, graphing flow in the pump and tank hydraulic rate, they should be exactly the same between the models. They're hydraulically equivalent. So if you have Bentley water gems, you can take advantage of the Scalibrator tool and pretty quickly simplify the model down. What that does is it creates, like I said, a hydraulically equivalent version of that full model by basically lumping your demands on the elements that are left over. If it has to combine any pipes in series or parallel, it combines them in such a way that they're hydraulically equivalent. So you can see, for example, at this junction, there's six demands that are contributing to that, and those were at one point further downstream. So this is the model that we're going to focus on today for our demonstration of some of the things you can do. So just to run through some of the basics of what you need to do if you're starting out with a water model that's existing, what kind of things do you have to enter to get it in a condition that's ready for transient analysis. So in this case, pretty common case here, you're trying to simulate what happens if this pump has an emergency shutdown. You're starting with the pump on, pump turns off, what happens? So the first thing you want to do is look at the pump properties, and a lot of different elements you'll notice, if you're used to WaterGems or WaterCAD, you'll see that there's a transient section in the properties. So those things can actually be entered as you're building your water model. Even in WaterCAD and WaterGems, you'll see these properties. So you can actually add those ahead of time as you're building the model so that it's actually even more so ready for Bentley Hammer. But if you don't have those things entered already, don't have to worry about it. There's just a few key things to look at. So for a pump, for example, we need to configure what that pump will be doing, which is to say, in this case, it's going to shut down after time delay. So I'm going to pick shut down after time delay as the pump type. We're going to choose 400 millimeters as the diameter and a time delay of 5 seconds. So this basically means that 5 seconds into the transient simulation, this pump will shut down, which means basically the power is cut off from the pump, and the pump will continue to spin down based on the momentum, but you will typically have some type of transient response as a result of that sudden pump shutdown. So in order to accurately simulate that spinning down of the pump, there are a couple of other properties that you need to enter. So if I go into the pump definition, you'll notice there's a transient tab here. So in the transient tab, there's a few things you have to enter. So you got your inertia, your speed, and your specific speed. So the inertia has a nice little calculator tool here. You click on this, and you can actually enter the brake horsepower and rotational speed, and it will calculate your inertia for you. And then I'll also enter the speed here. Specific speed is a bit of an advanced concept. This is more a function of the shape of your pump. There is an equation in the help that can help you estimate which one of these to select, but it basically allows Hammer to figure out how the pump can operate not only in the first quadrant, the positive head, positive flow, but out here in the other three quadrants, negative head, negative flow. Okay, so now that I have those things entered, we're just going to go with the default for the specific speed. So we're done with the pump. So the next thing we want to enter is the wave speed for our pipes. So you'll notice when you look at a pipe, there's a wave speed property. So this is something that you have to enter for every pipe. So this is basically how fast a wave will travel in that pipe, which can be a significant factor in how the waves reflect and interact with each other. So it's something that you want to make sure you get that accurate. It's a function of a couple of different things, your pipe material, how it's supported at the ends, how thick it is. Luckily, Hammer has a nice little tool under the Tools menu, Wave Speed Calculator, where you could enter a couple of things and have it calculate and apply the wave speed to all your elements. So in this case, it's a pretty simple example. All of these pipes are ductile iron, so we're going to apply the same to all. So all I have to do is pick from the engineering library what our liquid is. So I'm just going to choose water at 20C. And then from our material library, we actually have some of the coefficients that you need already available in the library. So for ductile iron, for example, it has the Young's modulus and Poisson's ratio. So I'm going to select that. It's going to populate that, and we'll just assume a wall thickness anchored throughout, and it's going to apply to all pipes. So we'll click OK, and it tells us that it applied that to all the pipes. So now if we look at the properties, we'll see we have a wave speed entered. Another shortcut to that, and that kind of segues to our next task that we need, is to set up the transient specific calculation options. So if you go into analysis calculation options, if you're used to WaterCat or WaterGems, you're really just working under the steady state / EPS solver options. But there's actually a separate calculation option set for transient specific settings. So let's just go through a few of the basic things that you'll pretty much always want to make sure you enter. So looking at the transient calculation options, first thing you want to do is choose what points in the model, which is to say which elements you will save transient results for. So by default, it's not going to save any results for any of the elements. You'll only be able to look at profiles. So you want to choose some key points. So in the drop-down, I'm going to select selected points, and then from here, click the dot, 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 and then select from drawing at the bottom. So you don't want to select everything in the model. You want to select just your key points that you'll probably want to graph pressure or flow, or basically the points of interest that you want to look at. So I'm going to choose the pump, and this is a high point here at J4, and I'll also choose the tank. And then click the checkbox, and then the single arrow pointing to the right side to add those to the collection of selected items, and click OK. The report times basically tells the program how often to save results. So a report period of 10 basically means that it's going to save results for your graphs at every 10 time steps. And we'll just accept that default. So the next step is to decide if you want to specify a custom calculation time step. So Hammer actually calculates this for you and attempts to do a balance between performance and accuracy. So if you go under Analysis, Transient Time Step Options, let's calculate the initial conditions first. Analysis, Transient Time Step Options. You'll see that Hammer calculated this as your hydraulic time step. We're going to go, basically accept that for this demonstration, but you could, if you wanted to, override that and specify a custom time step. That can also be done from this option right here. So next thing is to set how long we're going to run the model for. So by default, it's actually in terms of time steps, but most people don't think in those terms. So we're going to actually choose based on time, and we can add a duration in seconds. So I'm going to choose 90 seconds for our simulation duration. So you want to make sure to run it long enough so that things will settle down a bit. So you're not only capturing what happens as the event occurs, but also how things settle down. So you want to run long enough so that you can see and make sure that things have settled down a bit. Okay, so the other thing that's really important here is this generate animation data option. So this allows you to, later on after you've computed the transient simulation, allows you to actually animate and really get a better visual of what, how things are interacting with each other during your transient simulation, and really helps you understand, what's going on and what you might need to do. So default is false, so I highly recommend that you choose true for this for pretty much any model. And in conjunction with that, what we want to do is set up some profiles. So we're going to do that next after we set up all these options. The other options here, most of the time you don't have to touch them. If you're just running a steady state simulation for your initial conditions, you don't have to enter a time here for initialized transient run at time. But actually for this example, we're running an EPS simulation where we want to choose which time to basically use as our starting steady state conditions. So to give you an idea, I'm just going to graph the pump here along with the tank. Right click graph. So here we can see it's pretty typical. You got your tank is draining, the pump turns on, the tank fills, and then kind of cycles back and forth. So what we want to do is make sure that we're starting our steady state simulation for Hammer at an appropriate time. So for example, 7 hours is when the pump is on. So what we can do is initialize the transient run for time step 7, And that way, we're seeing, the pump is starting on, tank is up near the top, and then basically what we're going to see in Hammer is, what happens between this time and this time. So like I was saying, and for just a standard steady state, all you see is, okay, at one time, pump is on, the next time, pump is off. You don't actually see the details of what happens as a result of any transient effect between those time steps unless you use Hammer. So let's go back to those calculation options, and we're going to enter 7 hours for this. And then getting back to that animation data, so along with that, we want to make sure to specify any profiles that cover the areas of interest. So I'm going to go to Profiles, that's also under View Profiles, and click on the New button, select from Drawing. So what you want to do is select the area of interest that you're interested in seeing the transient effects of. So for this model, it's pretty straightforward. It's just one long line. If you have a more complicated model, or for example, that full model where things are a little bit interconnected, you may want to make a few profiles that cover different sections so that you can check a few different key areas. So it's really easy to make a profile. I'm just going to start at the upstream point, the reservoir, and then click on the downstream point, the tank, and it draws the profile for me. So I click the checkbox, Open Profile, and here we have the initial conditions profile. Okay, so Hammer will use this to generate animation data for results after the transient simulation. So we're going to give this more appropriate title, so we'll just call it full. Another thing you might want to do at some point is make maybe a more detailed view, for example, from this reservoir out to here, make another profile there. And for this one, I'm going to call this one pump detail. So if you have a really long model, several kilometers, something to the point where, when you're looking at the full profile, you don't really see that detail, you may want to consider, adding a few more, focused in profiles. Okay, so now we're ready to compute the transient simulation. So the first thing we want to do, I've already computed the initial conditions, and that's this button. Next thing we want to do is validate. So that's this button. That's going to check if we made any mistakes. Okay, so we didn't find anything of interest. This is one that we can ignore. So we're basically ready to run. And I will go ahead and click the regular compute button to compute the transient simulation. Okay, so when that's done, you get the summary here that has some statistics on max and minimum pressure, but this doesn't tell you a whole lot in terms of visualizing exactly what's going on. So, taking a step back a little bit, so what we've just done is basically ran a simulation to see what happens when these pumps shut down without any kind of protective measures. So maybe this is the proposed system or the system as it's working as is. So we'll consider this sort of a no protection situation here. So in order to view your transient results, what you do is you use a tool called the Transient Results Viewer, and that's from this icon here or from Analysis Transient Results Viewer. So you have 3 tabs here. The first tab is for basically viewing your profiles, and the other 2 tabs are for graphs. So I'm going to take a look at the profile first, and you'll see that we have both the full and the pump detail profile available. I'm just going to go with the default here of a hydraulic grade and air/vapor volume. Click Profile. Make this a little bit bigger for you. Okay, so what this is showing you is what we call the transient envelope. So the red line and the blue line is your maximum hydraulic rate and your minimum hydraulic rate over the course of the transient simulation. So you can see here, the green line is your ground elevation, black line is your starting hydraulic rate. So there's a high point right here, and we can notice at the top here there's a volume reported, and this is a vapor volume. So I'm going to go ahead and animate this. The pump is over here on the left side. So you'll notice when the time gets to 5 seconds, you'll see the transient event curve. So 1, 2, 3, 4, and there's our transient. The wave propagates downstream, and I'm just going to pause it right there. You'll notice that as the wave traveled downstream, it pretty quickly dropped below atmospheric pressure at this high point here, and it got down to a point where it exceeded the vapor pressure limit of water, which caused a vapor pocket to form here, and that's what you see forming. So I'm just going to inch forward a little bit so you can see that that vapor pocket continues to grow in size, but also notice this wave, as it reflects off the end of the system, it comes back, and then the vapor pocket senses the positive pressure returning, and it starts to diminish. So when it gets to the point where it's just about gone, you'll notice a certain phenomenon here. So see the spike in hydraulic rate? So this is a phenomenon that occurs when you have the two water columns on either side of your vapor pocket basically slam together, and the effect is similar to an instant valve closure where you have, just like with the pump shutdown or a valve closure, a sudden change in momentum. So the water is nearly incompressible, and it's basically crashes together like a head-on car crash, and that causes a severe transient. And I'm going to go ahead and click play here, and you can see that bounces back and forth, and that's basically the cause of our maximum pressures that we're seeing in most of the model. And then as it bounces back, that reflects as a low pressure wave, and that also causes some lower pressures at points. So we can see that this system probably is in need of some kind of transient protection method, some kind of measures to protect against these problems. This could cause some major problems here. So I'm going to go ahead and close this. Now that you've seen the skeletonized model and how quickly I was able to enter things and get it to a point where I could see some transient results, let's switch back to the full model here. And I just want to make a few points to reinforce why it's a good idea to skeletonize the model if possible. And basically, if you're dealing with the full model, there's that much more configuration in terms of the transient simulation. So we talked about like entering the wave speed of your pipes. Well, if you have full pipe model, then you have to consider, okay, these are ductile iron pipes here, but over here, these are PVC, and then there's some steel pipes over here. So you have to, do a little bit more work in getting your wave speeds entered, to accurately simulate what goes on in this part of the system. A couple other things you can run into. For example, this pipe is closed here, and we have a pipe next to it with zero flow. Sometimes if you have pipes with zero flow, just due to the way that hammer has to convert the calculated head loss to a friction factor, and it uses that during the transient simulation. Long story short, you can sometimes run into some additional challenges and some further massaging of the data that's required for those situations. Whereas if you're dealing with a skeletonized version, that's not something that you have to worry about. Also, there's some PRVs here. During a transient simulation, you have to kind of specify, are those able to actually dynamically modulate during the transient simulation? And if so, how fast can they react? So you have to set up some coefficients, things like that. So there's a couple other little things to watch out for, but the basic point is that the bigger the model, the more time it's going to take to prepare that for a transient simulation, with possibly diminishing returns. Because, for example, in this case, you've got a pump station. This is basically your main line out here to the tank, what we have in the skeletonized version. And that's really going to experience the worst transients as a result of a pump shutdown. And when you get way out into the model way over here, the transient waves tend to dampen out, especially when things are looped around, and just the friction tends to dampen things out. So usually, it's not going to be a problem way out in the system. So by focusing on the skeletonized version, you can be pretty confident that if you can mitigate harmful surges in the skeletonized version, then the rest of the model that you didn't include should be okay.